Good morning. Did I get that right? Okay, is that where you usually sit? Okay. Oh, no, you're a roamer, or that's your spot? Okay. Good morning, everybody. It's nice to see you all this morning. The local time is 9:48 in the morning, and we will begin our discussion on Earth interior at 10 o'clock local time. That's a little bit more than 10 minutes from now. Go ahead and scrub ahead if you're watching the replay of this, but otherwise, you are looking live on a Friday morning here in Ellensburg, Washington, USA. Thank you for joining us, and let's double check and make sure that we are functional and everything is in order. Mark says it's 5 by 5. Ned is in the house. Damn right, son. San Jose, California. Hello, Russell and John and Cindy. Lightning strike. Where are you viewing from this morning? Oscar, San Diego. I know where you're watching from. Some of these are regular names. Carol's a regular name. New York City. Brussels, Belgium. Good afternoon. Dayton, Ohio. Finland. Scrolling too quickly now. I saw Las Vegas scroll by. Sweden, hello. Devon, UK. Manchester, UK. London, UK. Oh boy, we got the Brits in the house. McKinleyville, California. Vancouver, Washington. Texas, Texas. Lethalese in Marysville, Washington. Birch Bay. Longwood, Florida. Squim, Washington. Finland, hello. Stevens Point, Wisconsin. Oh, God, cripes, those Packers. What happened? I think the head coach got a little overwhelmed, personally. Wasn't up for the big moment. Cute little guy. So young. Orange County, Georgia. Must have been California. Minnesota. Jurassic Coast, UK. Lubbock, Maine. Hello. Durango, California. No. Durango, Colorado. Special shout out to George. George sent me 3 separate emails in the last 24 hours. He is another lighting consultant, camera setting consultant. And I think he's onto something. I'm not yellow, and yet the settings were identical to what we had yesterday with the camera and the light. Everything is identical. So George said, it's the color of your shirt. So he says, I'm camouflaged right now. You can't see me, right? The Emilys are snickering right now. Emily 1, Emily 2, snickering. Christina. You can't see me. People are showing up for class and then they're just turning around. It's like, there's no instructor. There's no instructor. Tim's just walked in. He's having a hard time figuring out what's going on. All right. So we'll keep testing it, George. I don't think I want to wear a green shirt the rest of the quarter. I don't know. Maybe I do, but maybe the jaundiced yellow look is when I wear blue shirts. A couple more hellos. We have good work to do today, important work to do. I'm looking forward to working with the group. We have about a quarter of the group that's here. Jordan, did you want to see your test result? Good. Come on up. I'll be right back. Come on this way, would you please? I've got you over here. Missed you yesterday. You okay? Mm-hmm. All right. Oh, you watched it. Oh, God, where are you here? I don't think think I should really let you paw through these, but there you are. So take a look. You know, since you watched it, that I need to hang on to it, but there's the answers and there's the spread, and good effort to start with. Keep it going. Hot mic. A couple more hellos to folks. Florida, good morning. Where else? Where are we talking? Iowa. I'm in the way of some of the students. They're copying down the outline. Jamie Zoe. Are you better today, Jamie? I do apologize. Aarhus, Denmark, Avery, California, Aberdeen, Scotland, Council Bluffs, Iowa, Coeur d'Alene, Idaho, Knoxville, Tennessee, New York, Turnbridge Wells, UK. I hope everybody's doing well in places that are still completely locked down. I hope, one day at a time. We'll get there, but I'm sure it's a major struggle, especially this time of year. Dublin, Wasilla, Alaska. Do you know the Schleich family? One of the daughters is dating my son in Wasilla. Fairbanks, Alaska, Oak Harbor, Washington, Gran Canaria, Spain. Hello, Alejandro. Okay. Still got a few cookies left from Joe. Thanks again, Joe, for your hospitality and your generosity. Mumbai, India. Hello, amazing Indian. You are amazing for being here this morning. Cologne, Germany. Now I'm just grabbing the most exotic locales I can find. Narum, Denmark. Forks, Washington. That's exotic. Las Vegas. All right. All right, I'm going to go visit with some students, okay? Thanks for joining us this morning. Have I said that 3 times already? Good, I'm contractually obligated to thank you. Thanks for joining us. Whoops, I went past the limit. All right, Tim's in his spot. Jack, I don't know anything about you. I'm coming toward you. That's plenty of warning, huh? And young man, I've forgotten your name. Alex.
Yeah.
Have we chatted?
Not yet.
Okay, well this is it, Alex. All right. So Jack and Alex, where are you guys from?
Vancouver. I'm from Puyallup.
Puyallup and Vancouver. So you're both West Siders. You must feel weird it's not raining every frickin' day for weeks on end. All right. Well, is this your first winter over on this side of the mountains?
I'm a senior.
Oh, you're a senior? What are you majoring in?
Geography.
Oh, you are. Have you had to specialize in like more physical geography or cultural?
Yeah.
You are. Okay. Wow. So you're feeling a little out of sorts right now. You're not looking into a computer screen at the moment. Yeah. Who's running that GIS scene now? Is there one person who's kind of the main advisor? And
Sterling,
yeah. Okay. What do you think of him?
He's cool.
Good. That's a good answer. You're being recorded right now, by the way. Well, good. So you're graduating in June or later or earlier?
Next fall.
Next fall.
Yeah.
Christmas time, maybe.
Yeah.
Yeah. Good. And you're here for a gen ed requirement, I assume? Yeah. Okay. How about, oh, good Lord. Hang on now. That's Jack. And this is Alex. Sorry.
Yeah.
So Alex, how about you? Is this your first?
Yeah, this is my first one.
Your first year student here?
Yeah. A lot colder in there over there.
It is a little colder, isn't it? Yeah. Yeah. It gets down there. Yeah. We haven't really had the real nasty cold stuff, but yeah. Are you living on campus?
Yeah, in Quigley.
Oh, really?
Yeah.
And is it kind of a full scene or like?
There's I think 10 people in the entire dorm.
Oh my
So,
God.
Not that many people.
So, well, good. This is kind of a relief to be in a place with other people, right? Even though it's really super quiet right now. we continue to build. Well, good, Alex. Good to meet you. Good morning, Eve. Okay, it's foggy. It's cold. I'm gonna really come to you today. I'm gonna need some from you today. Okay. We're gonna do some back and forth, and no pressure, but let's get something built here. Casey, good morning. I got everybody's name right now, I think. Emily 1, Emily 2, Jordan, Isaac, and Aiden. You guys can really screw with me and switch spots at some point this quarter. That would be fun. But Christina's kind of cornering the market on that sort of mind game stuff. That's good. And it is your hope. Yeah. Michaela is there. Right? And that's it. And then there's Fred, and there's Joan, and there's Agnes, and there's Gertrude, and there's... Now I'm screwing with the live stream audience. What? Gertrude? There's a 21-year-old young gal named Gertrude? Oh, names go out of style. We don't have a Gertrude this quarter. Letha Lee finished her warm noodles, everybody. Letha Lee, she just finished her warm noodles. You heard it here first. Rupert, hello, Port Deposit. Port Deposit, Maryland. Dareth, I missed you, and now I have found you. Green Steve, yeah, okay, man. Union, Ohio, Rhode Island, hello. Calogero, hello from Switzerland, what up, homie? Geo Daddy, yeah. Peter says, welcome, CW students. Oh boy, we haven't had a Mason sighting yet. We got 1 minute. Or a Pedro sighting. What are we going to do? You guys got to fill the void. Hello, Sharon. Waterloo, Wisconsin. Old Uncle Don Gruber used to coach in Waterloo, Wisconsin. Took him to the state tournament, I believe, back in the 1960s. You might have to Google that one. Back in the vintage when Dick Bennett used to be coaching at Eau Claire Memorial. Vienna, Austria. Hello, Richard. Okay, it's 10 o'clock. We're going to get going right now. Okay, students, I promised that I wasn't going to comment on this, but I am. Okay? It's the day after you give back the results of a midterm, and there's always struggle in attendance, but here she is. Great to have you here. So I am especially impressed that you are here and locked in and ready to go. We're not even going to think about the results of the first midterm, but I'm going to come to you hot right now. I'm going to come to you right now, and we're going to get a dialogue going. And this is especially important, these next 3 lectures. So, you made it here. That's step 1. Step 2 is to be totally here and to be totally engaged with what we're doing. And to confirm that, I want to have a dialogue with you right off the bat. So here we go. We're starting. The title of the lecture is called Earth Interior, but I want to start with a concept called Pangea. Have you heard of it? Thank you. That's a promising start. Describe Pangea to me, and who taught it to you? Do you remember who, or what level, or what do you know anything about this Pangea business? Somebody.
Like a previous continent. It was like the previous continent on the Earth, and it eventually broke apart and turned into what we have today. And no, I don't remember where I learned it.
Oh, hope you're setting the stage beautifully for this. Thank you for coming with that energy. So Hope used the phrase a previous continent, and then it kind of broke up or something. Who wants to add to that? What do we mean previous continent? What do we, Michaela?
It was just like all the land masses just mashed together as one, and they broke apart over a period of time.
Beautifully done. So Pangea, so we are talking about the content, by the way. I'm weaving this into a conversation with you all, but we're covering ground. So Michaela has added that it was all the land masses together, like on this frickin' ball here, man. You know, this is our, whoa. You've got the outline now. We know this as the globe today. And we know the geography of these 7 continents. But we're talking about a time when all 7 continents were connected. And there was a time on planet Earth where there were all continents glued together, and therefore we had one continent and one ocean. I'm holding up 2 fingers. Mistake. We had one continent and one ocean. Has that dawned on you? Maybe if you know Pangea and the concept, has it really sunk in that our planet, for 100 frickin' million years, for 100 million years, that's not just a couple of Tuesdays, our planet Earth, we know for sure, had one big continent and one big ocean. And we name that continent, it's a supercontinent, Pangea. So what do you suppose these numbers 300 and 200 are trying to say? Let's not overthink it. What do I mean? How do those dates correspond to Pangea? Somebody verbalize that for us, please. We're off to a good start. Somebody else. This is the 100 years, thank you, Aiden, that the Pangea existed. MA is millions of years ago, correct? You're Isaac? God dang. All right. So let me give you a little bit more verbiage, and I don't know why, but students screw this up. There's a few things that students always mess up on exams or quizzes or even in our discussions, and it doesn't seem to matter how I phrase it, it just doesn't stick for some reason. So I'll try with my own words. 200 million years ago is when Pangea started to break apart. So I think we all know the concept. I'll show you maps in a second. We all know the concept of Pangea now, one supercontinent. And that one supercontinent of Pangea started to break apart. It started to break into pieces. It started to break into, well, I don't know, it's like 7 pieces, like the 7 continents we have today. That breakup, and that's the word I want to use, that breakup of Pangea, with my hand gestures like this, started 200 million years ago, and in a way, Pangea is still breaking up today. Do you remember yesterday? The fingernail thing? These continents are moving 2 inches a year, every year. Well, that's the rate at which these supercontinents break up, and how the rate at which these continents move. There's a global map of the world right there on the wall. Every one of those continents is moving 2 inches a year. So it's a slow motion breakup of a supercontinent. So what's the 300? Yes. Christina says when it came together. Now this is where we start to speak different languages. You're not Christina?
I didn't say that.
Yeah. I didn't say that. You thought I said that? I didn't say that. She said that. I didn't say. Okay, that's my bad. Good. Nice. No. Oh, this is so weird. You should all be up here in the front, Mike. You know, this is so weird. Okay. I guess this is why students screw this part up. If you're aware of Pangea, maybe it's until right now that you've thought hard about this, and Pangea was not the original configuration of planet Earth. Maybe this is even how it's taught K through 12. I'm not sure. The focus is on Pangea breaking up. Like there used to be a supercontinent and no longer a supercontinent. But nobody talks about before Pangea. And there was a before Pangea. So before we lose each other, Hope, a.k.a. Christina, said 300 million years ago, Pangea was assembled. Let's use that word, like a puzzle. Yes, it's the trite analogy that's always used. A jigsaw puzzle, and you put the puzzle pieces together, it makes Pangea. Boring. It's been done a million times. But it is true in this sense that we are assembling this Pangea. We are assembling this supercontinent, and all the pieces did fit. All the continental scraps did fit together 300 million years ago, stayed together for 100 million years, and then started to break apart 200 million years ago. I feel bad for some of the people who are not with us this morning. Not really. But we're going to be talking about these dates casually from this point forward. And you'll be in on the ground floor on what those dates mean. So do we know anything about what happened before 300 million years ago? If I'm saying that Pangea was a thing, and I am, and I'm saying that there was, I don't know, like there was something before 300 million years ago, yes. I don't want to spend the whole hour on this. But there's actually, if you go back far enough in geologic time, a supercontinent cycle. We do live on a ball. And if we break up a supercontinent like Pangea, another way to view that is we're heading for the next one. This is like a global party, a global continent hookup with a cycle of hundreds of millions of years between supercontinents. So what I'm trying to say is, I'll give it to you quickly. I don't know if it's even worth writing down. The supercontinent before Pangea was Rodinia. And the supercontinent before Rodinia was Columbia. We've given names to these frickin' things. And we're going back way into the Precambrian, way at the bottom of page 1 on your yellow book. And of course, as we go further back in time, we have less and less good evidence to reconstruct it precisely. But there's enough evidence to make sure that we've got that. So this is, through time, a cycle of breaking up a supercontinent, weird geography, weird to us, get all those continental scraps back together, make a supercontinent, hold it together for a while, bust that up, different global geography, weird to us, make Pangea, and in the last 200 million years, we have slowly been breaking apart Pangea, and yes, heading to the next one. I'll be more precise because I'm losing a couple of you already. The Atlantic Ocean has been growing in width every year for the last 200 million years. Can you find the Atlantic Ocean on that map over there? Tim, hop up, would you? Where's the Atlantic? Which one's the Atlantic? Atta baby, that's the Atlantic. Can you point to the Pacific Ocean, please? Yes, good job, right. So we can all agree the Atlantic Ocean is smaller than the Pacific Ocean. But if we go back to 200 million years ago, there was no Atlantic Ocean. Tim, I'm going to use you again. Can we point to North America and South America, please? North and South America. And can we point to Europe and Africa, please? Europe and Africa. And we can bring those two Americas and that Europe and Africa and bring them back together to where they were connected during Pangea time. I'll do something with the laptop now, and the live stream audience can follow as well. But that's helpful, I think, to see that map right there, because during Pangea there was no Atlantic, and the Pacific was much larger than it is today. The Pacific is still our largest ocean, but it used to be bigger. So here's one more way to say it. In the last 200 million years, the Atlantic Ocean has been growing while the Pacific Ocean has been shrinking. And that's going on every year. Pacific a little smaller, Atlantic a little bit bigger. Pedro is here, thank God. Thank you, Tim. Do you have questions? You must have questions. This must trigger, even on a foggy Friday morning, a couple of thoughts. What do you have? Come on, what do you have? Tim. Yeah. We're not to tectonic plates yet, but you are correct. So did you want to go somewhere with that? Yeah. A little premature, but yes. Yes. We're focusing right now purposely on just the continents and just these bodies of water called oceans. Now, I had a real hard time with the document camera last time, so I'm really going to make sure that I'm set up for both you and the live audience, because we're going to do a fair amount with the world map today. So that's good for you, and that's pretty good for the guys at home as well. Good. Okay? Yeah, please. Casey.
Is it possible that before these cycles, there was no continent and it just formed out of a tectonic plate movement?
Well, there's a question. Casey wonders, is there a time before this cycle? And did you also say, is it possible the continents haven't always been with us on the planet?
Yeah, it was just like 100% ocean and they formed out of tectonic plates.
Yeah, wow, great thinking. Early Earth is something I've always ignored, like going back more than 1 billion years ago, because we're so far back in time that there's hardly any rocks to look at from those times. But given that statement, yes, many geologists, maybe all, assume that our original planet was nothing but ocean, and that our original planet Earth, 4.6 billion years, had no continental crust on it. And if that's true, then we're getting into basic questions like, how do you make continents? And then if we eventually form these continents, when do we start our cycle of supercontinents? Can't do it, man. That's too much, but that's good in a good way. Okay, I feel like I'm really connecting with about half of you, and the others, I can tell you're gone mentally. So let's hammer you now, or stimulate you now, with images. So there is a map of North America, South America, Europe, and Africa, and here's the growing Atlantic Ocean in between. When did Pangaea get assembled? 300. When did Pangaea start to break apart? 200. How old is the Atlantic Ocean? Less than 200 million years old, right? It was a baby back 200 million years ago, just starting to form as the continents, North America and South America, started to rift away. That's Pangaea. We have an actual map. Can you see the equator? Can you see that Florida is in the southern hemisphere? We know exactly what that Pangaea looked like. We know where it was positioned on planet Earth. Kind of fun. And I'm coming to you again, warning, in a couple of minutes, because I know some of you have been taught at some point about the evidence we have for this. This is not just an idea. But it was just an idea 100 years ago. On your outline is a name, Alfred Wegener. You've already written it down. And Alfred was a German climate scientist. He wasn't a geologist. But he was working with world maps, and he noticed that he wasn't the first, by the way, but he was the first to propose this as a scientific idea. He noticed what I'm sure you've been taught, that the continents look like they are jigsaw puzzle pieces, and it looks like they can be fit together. Like, let's find this map here. So you can see that the east coast of North and South America makes a capital letter S. And the west coast of Europe and Africa makes that same capital letter S. And I think first graders can look at that map and wonder, is that a coincidence, or can I put those puzzle pieces back together? Well, that was Alfred Wegener officially proposing Pangaea. Alfred Wegener is the name. I don't give you many old dead guy names, but Alfred Wegener is one of them. He was the first to propose Pangaea as a thing, I think in 1912. I may be off on that date. And he was laughed out of the room, whatever scientific conference it was. Who is this German guy? Pangaea? And he was laughed out of the room because, of course, you can't move a continent. That was the scientific thought of the day. You can't move a continent. What's this guy talking about? But Alfred was painstakingly taking what was known about the position of the continental shelves, which are the flooded portions of continents, and they fit together even better than the modern coastlines that we have today. And this was not an animation from Alfred's time, but this is essentially an animation that I'm sure you will enjoy, because every group I've showed this to, young and old, loves this animation, and I have it on a loop. It's going to go back and forth. But it is demonstrating continental drift. I know you've heard that phrase, continental drift. That's Alfred's idea. Alfred says, I think there used to be Pangea, where all these puzzle pieces fit together, and obviously they're not fit together anymore, so I think the continents have drifted away from themselves to their present position. Here we go. You ready? I'll just let you watch it first. I'll try to keep my mouth shut. I'll watch with you. I'll come back over here with you. So the dark green is the familiar continents themselves. The kind of yellow or light green are the continental shelves, the portions of the continents that today are underwater. Okay, here we go. We just broke apart Pangea, right? So that started about 200 million years ago. And this is the movement of these continental pieces over the last 200 million years until now. And then I put it on this loop so then it goes back to 200 million years ago. So I'm just showing you on this loop the breakup of Pangea and then going back to Pangea time. Who's got questions? Tim.
So, I've noticed two things. First of all, India was once attached to Antarctica.
Let's focus on that. So India, so some of us are geographically challenged. Look at this cute little India guy. We got some live stream viewers from India. So India used to be connected to Antarctica, Tim is noticing. And then at some point in the last 200 million years, there's 200 million years right there, right? 200 million years. Start to break it apart. And we're focusing in our part of the world on the opening of the Atlantic Ocean, but Tim's noticing India swimming pretty damn fast, by the way, through the Indian Ocean and eventually connecting with Asia. Did you want to ask about that, or did I cut you off? Just an observation. Okay, you got another one?
Yeah, and then the other one I noticed is kind of the area, I guess, where Panama would be.
Right.
That's North and South America.
Yeah.
It kind of just pops out of the ocean.
It pops out.
Is that like igneous,
I don't know.
or are we just like, well, it's there, so let's throw
Right.
it in there?
So Tim's also noticing that Central America just pops out of nowhere, and I'm sure that caught your eye. It always catches people's eye. I've always meant to look this up. I don't know. I don't know if this is a glitch in the animation or if there really is some sort of geologic story for forming the basement rock of Honduras and Costa Rica and everything else. I assume you know where I'm talking. Eve. Ooh. Eve says, because India used to be at close to the South Pole, is that what you mean? Was India under ice for a time? Yes. How did you know that? You just... Yeah. That's also true. So Eve is doing some very impressive thinking at the moment. Number one, we have glacial deposits in India from this time, during Pangea time. And we know we have that because India used to be much further south than it is today. It's pretty hard to come up with evidence for a big glacier at the equator. And then also, Eve is mentioning, well, does that mean that Antarctica hasn't always had ice on it if Antarctica hasn't always been at the South Pole? And that is also true. Pretty good stuff, huh? Aren't you glad you came? Couple more before we move on? Haven't even gotten to the Earth interior. I'm just kind of setting you up. Hope.
Australia is also hanging out really far down south. Further south than Antarctica.
Yeah. Yeah. Yeah, Antarctica is also hooked onto Antarctica. Australia is also hooked onto Antarctica, and it's also hanging out there down by the south. I don't know about glacial deposits on Australia, if that's what you're getting towards. But my point so far in the lecture is this was an idea 100 years ago. It was a laughing stock. Nobody in science, quote unquote, accepted it. And this guy, Alfred Wegener, spent the next 20 years of his life looking for evidence to prove that this was the thing. And it's a sad story. He died in Greenland on one of his expeditions and never saw his ideas accepted. But I wouldn't waste your time with his ideas if we didn't accept them now. So continental drift as a concept originally proposed by Alfred Wegener is not an accepted idea. Please take notes on this. Continental drift is not a complete idea, continental drift, because continental drift assumes that the continents are moving through the ocean floor somehow. I'll say it a couple more ways. Continental drift is not accepted scientifically because technically continental drift assumes the continents are moving through the ocean floors. They're like plowing through, like some sort of big snow plow through the ocean floors. So nobody in science accepts continental drift, but they do accept a modified continental drift called plate tectonics. And I feel the energy is great right now, so I'm just going to cut right to it. The difference between continental drift and plate tectonics is that it's not just the continents that are moving. The ocean floors are moving also. And that's what a tectonic plate is. A tectonic plate is as we'll look more carefully in just a second, a tectonic plate is the fundamental unit of motion as opposed to the continent as a fundamental unit. I'm going to say it one more time as succinctly as I possibly can. This animation is sexy, but it's just looking at the continents doggy paddling through the oceans. That's continental drift. But today we realize it's more than just the continents that are doing the movement. The continents are connected to parts of the ocean floor, and that continent-ocean floor pair is moving as a tectonic plate. That's where we're headed by the end of today. Okay, I love your energy now, and I want to continue with you. I'm not going to come, since we spent more time than normal on that discussion, I'm not going to come to you with evidence for Pangea. I'm going to go through it very quickly with you. But this, no, we're not doing it. Okay, what evidence do we have for Pangea? Number one, we're just going to make a list and I'll just have you jot it down if you don't mind. I'm not going to take the time to write it all out on the board. This is Alfred Wegener's evidence for continental drift. 1, the continental shapes match. We've already hammered that pretty hard. 2, the bedrock in these blue areas are identical. So let's slow down and look at this. This is a map of today on the left and of Pangea put together on the right. And the areas in blue, let's not even get into the details of the kinds of rocks. Let's just say that the bedrock in these blue areas, and look at this, this is Greenland, Norway, Ireland, Portugal. Again, many of our live viewers from around the world, if you're in this blue area, you have identical bedrock to these other blue areas. And today they're separated by thousands of miles of water. But Alfred said, look, I've spent the last decade in the 1920s visiting all these spots around the rim of the Pacific Ocean. Out of all spots around the margin of the Atlantic Ocean, they're all the same rock. The only way to make sense of all those identical rocks is to move the continents back to their original Pangea location. And in fact, this was a mountain range. This was a major mountain range that has been broken up. We've already talked about that. Remember, we're talking about the Appalachians forming and then the Appalachians getting split apart. Same concept of taking things that today are very separate from each other, but make sense if you bring them back together. glacial striations. This is Eve's specialty. Looking at evidence of glaciation, glacial striations. You remember those scratches or those grooves left by ice sheets? Well, if we go back to Pangea time, today, can you see this map? Pretty well. Today, in purple, and those little arrows are all these places that have glacial striations from the time of Pangea. And again, those striations don't make any sense where they are on their current place on the planet. And they also don't make sense because they're separated from each other. But if you bring all the continents back together to Pangea, then they're all part of the same ice sheet. This isn't hard. But we have what? Continental shape, identical bedrock, separated by oceans today, identical glacial striations. Even fossils. I'm no fossil person, but whatever, you can see them. These fossils here are very rare. They're from the time of Pangea. Is it a coincidence that this thing has only been found in portions of Africa, India, and Antarctica? I guess it's possible, but it's more likely to have those places where we have that rare fossil connected by moving the continents back to their Pangea position. You got it. Okay? We're going to take a little break, and I'm just going to transition you now to the real heart of today's lecture. Thank you for your energy. Okay, the story continues. Alfred passes away in the early 1930s, and with his passing, continental drift goes away. So it never really had a whole lot of traction anyway. But people are definitely not talking about continental drift or teaching Pangea in any science class all through the 1930s and the 1940s. Nobody. Then we have a world war. Have you heard of it? World War II. And there's a bunch of new technology that shows up to look for submarines. Thankfully, the war is done in 1945, and now we have all this fancy technology looking for subs. And they're like, okay, well, let's put this technology to use. Let's make a map of the Atlantic Ocean floor. Let's not look for subs, but let's use this wartime technology for the first time in the late 1940s. I'm yelling now a little bit because I'm excited. Are you aware that 2/3 of the Earth's surface is ocean? And are you aware until the 1950s? That's not that long ago, folks. 1950s. Until the 1950s, we knew nothing about the ocean floors, had no idea what was down there. Alfred's time, the assumption was it's just like the oldest crust of the world and it must be super flat and boring down there. It's anything but flat. It's anything but boring. What? The ocean floor. We, with this technology in the late 1940s and early 1950s, found mountains, found mountain ranges. Some of the biggest mountain ranges in the world are underwater. And this whole set of discoveries from the ocean floors brought all this continental drift stuff back to the fore. In case you're unaware, I'll just finish the timeline. 1960s is when everything is totally put back together mentally and in scientific papers. And so you know plate tectonics, but that phrase, plate tectonics, which we're heading to before we quit today, becomes a thing in the 1960s. I was born in 1962, so I'm basically the same age as plate tectonics. I know I'm an ancient person compared to you, but I can still walk and talk. I'm not that old. And so plate tectonics, which was a revolution in science, took hold in the 1960s, using those ocean floor discoveries. That's the context for this. Now, we go to the yellow book, we lose the broad storytelling, and we get into the nuts and bolts. But I hope that story time hour was enough to get you going. By the way, if you do, you are serious about continuing in the class and improving over your first exam, Here's a tutoring opportunity. These are posted all over the lab room. We call them open hours, but sometimes I don't think people go because they don't even really know what open hours means. These grad students are in there just twiddling their thumbs. They're waiting to help somebody learn lab stuff or lecture stuff. So Zach and Ben are both very bright. They're in there sitting there by themselves during these hours every week. Go in there and get some help if you need it. Work with me if you need it. There's plenty of opportunities to learn this stuff if it doesn't stick the first time. Okay, yellow book, page 17 and 18, housekeeping first. So I would like you to go to page 17 and page 18, please. And I'd like you to add a couple things. We're going to get into just a little bit of geophysics. So I wanted to do enough broad stuff to kind of give you a reason for caring about the geophysics. So to the top of page 17, would you please add a title? Earth Interior by Silica Content. Headline on page 17, Earth Interior categorized by silica content. We need to discuss what that is, but that's our title. And if you flip over to page 18, that's the same planet Earth. That's also talking about Earth interior, but it's looking at physical properties. The heading for page 17, silica content. The heading for page 18, physical properties. And now that we know the context of Wegener and ocean floor discoveries, I hope that this will go quickly. Okay, page 17. What does it look like? It looks like this. You've got it in front of you. These are terms that I think we all know. The Earth has a crust, it has a mantle, and it has a core. What is up on top? The surface. There's a couple, that's you and me walking around with our cute little hats. The boundary between the crust and the mantle is called the moho. M-O-H-O. It's named after the guy who discovered it. A guy in Eastern Europe called Dr. Mohorovicic. Mohorovicic. Come on now. Mohorovicic. Yeah, come on. All right. Obnoxious. The moho is a boundary. It's not a layer. It's a sharp boundary between the crust and the mantle. And you'll notice that in certain places, the moho is shallow. It's only 5 kilometers below the Earth's surface. And in other places, we'll be more specific next week, the moho is 70 kilometers thick. That's why that boundary is so squirrely. And then we go to a boundary between the core and the mantle. Yes, there's an inner and outer core. We don't care. This number here is the depth to the center of the Earth. Okay. These terms and these concepts were known during Alfred's time, when he was trying to convince people that pieces of crust were moving around, continental drift. And all we knew at the time was that the silica content was different between these 3 layers. According to the title you just put on this page, crust, mantle, and core are silica composition terms, and you're right. You ready? There's a lot of silica in the crust. High silica. Compared to the mantle, medium levels of silica. Compared to the core, low levels of silica. You're like, why am I writing something down? I don't know what the hell silica is. I don't know. Maybe just do it. Lots of silica in the crust compared to the mantle. And the mantle has more silica than the core. One more time. High silica, medium silica, low silica, crust, mantle, core. Silica, as we'll learn more next week, is a combination of 2 elements, silicon and oxygen. So silica is just slang. It's just jargon. Silica is a combination of those 2 elements, silicon and oxygen. If you've got a great memory, our absolute age date lecture had the stuff we got back from Denver, and we had a bunch of silicon and a bunch of oxygen, if you recall. So there's silica in everything. Silicon and oxygen dwarf all the other elements. Our Earth is almost all silicon and oxygen. So we're just talking about the relative amount of silica. So if you melt the crust, you get high silica rocks compared to mantle, compared to core. Well, this isn't going to help us move stuff around. That's my point. And Alfred passed away, and all we knew about the Earth interior was crust mantle core. And that's why nobody believed him. And actually, Alfred Wegener, the guy who proposed continental drift, made a tactical error in the 1920s. He wasn't a physicist. He didn't know about math, but he tried to propose how his continents could push through the ocean floor. And anybody with an analytical background immediately like, this guy doesn't know what he's talking about. So all of his good work, the evidence we were just talking about, all the stuff that matched on opposite sides of the Atlantic, that was tossed out too. So he did great field work, but he didn't have the quantitative skills or the discoveries of the ocean floor to make it possible to move stuff around. Okay? So at this time, page 17, we're going to use these terms down the road, but it's not going to be used in the terms of plate tectonics. However, if we turn to page 18, these are the terms that we now realize are incredibly helpful in understanding plate tectonics. Now, this is confusing because this is the same planet, and this looks like the same kind of a plot. But we're not looking at chemistry now. We're not looking at silica content. Instead, we're looking at, what does your title say? Physical properties. So the lithosphere of the Earth is 100 kilometers deep, all around the world. A lithospheric shell, the upper 100 kilometers. And physically, the lithosphere is cold and rigid. Those are the two general words I would have you ascribe. Subscribe? I don't know. I would encourage you to put cold and rigid next to lithosphere, and I would, for asthenosphere, which is the next 100 kilometer thick section, 150 kilometer thick section, I'd have you put warm and flowable. Not even sure that's a word. Warm and flow. Warm and flowable. Both of these are solid, but the lithosphere is cold, solid, rigid material, and the asthenosphere is warm, solid, flowable material. It's kind of like the big hunk thing from yesterday, but on a much, much grander scale, much, much bigger scale. Not talking about magma here, talking about solids, but the discovery of the asthenosphere allows us to understand. I'm going to finish the thought, and then I'm going to go back to the laptop with a couple of animations, because it should be unclear how we actually know this stuff. Have we really drilled down to all these layers? No. So how the hell do we know anything about them? That's coming. But let me finish my thought. A tectonic plate is a section of the lithosphere. Hell, I'll do it. If we take some sort of saw and we cut all the way through the lithosphere, we're going to make a cut that's 100 kilometers deep. That's a red line. That's a cut. Here's another cut. Here's another cut. What did we do? We just broke free two huge blocks of the lithosphere. Two huge blocks of cold, rigid material. That's a tectonic plate, a block of the lithosphere. That's a tectonic plate, a block of the lithosphere. It's a much bigger, deeper story than Alfred was talking about. Because a tectonic plate can have ocean crust and continental crust on the same raft, on the same block. But it's this physical approach to the interior of the Earth that paid off much more dividends, many more dividends than the silica content approach to the interior. Last comment. The asthenosphere is solid, but it's warm and flowable. That's a big deal. Because if we can break out two tectonic plates, and there's this silly putty or warm taffy or warm big hunk down below, this stuff can move. These tectonic plates can move. They're not anchored to the core of the Earth. So the discovery of the asthenosphere broke open the whole thing, allowed us to realize the dynamic nature of moving tectonic plates. And if you remember from yesterday, I still don't think we totally understand why these blocks are moving, but that's not what I'm focusing on right now. I'm talking about why it's possible to move these blocks around, because they're not anchored to the core of the earth. Who's got questions? No? I got 10 minutes. You're still here. You haven't run away yet. Let's do it. He looks for his advancer. There it is. So we know about all these layers inside of the earth by an indirect means, by looking at earthquake waves or seismic waves. So here's an analogy. This is an animation, hopefully without sound. This is a woman lying on her back in one of those tubes in a hospital. And we're looking inside of her brain. And thankfully, we're not drilling into her brain, but we're learning about the details of the structure of her brain in a CAT scan. And the analogy is we can learn about crust, mantle, core. We can learn about lithosphere, asthenosphere, not by drilling down that far. We can't drill down that far. But we can image. We can get reliable details from the inside of the earth, just like we can get reliable details from the inside of her skull. So we're learning indirectly by sending waves through materials. And now we're away from human brains and we're into the planet itself. So instead of making artificial waves, we look at seismic waves. Do you know how to spell the word seismic? S-E-I-S-M-I-C. S-E-I-S-M-I-C. Seismic. That means earthquake. So I'm going to show you a couple more animations right now that look at seismic waves. Waves of energy traveling through the crust and the mantle and the lithosphere and the asthenosphere, kicked off by earthquakes. Let's do it. There it is. There's the word, seismic. Don't worry about the other word. So this is geophysics, which I know next to nothing about. But these little stars are earthquakes that are popping. And now we're going to cut open the earth and we're going to zoom in and we're going to look carefully at all those seismic stations that are up here to record the arrival of these seismic. Oh, there's an earthquake. Now all those blue lines are these waves of energy coming away from where the earthquake happened, and we study the path, the speed of those seismic waves. So you now know how to spell the word seismic. Let's do this one. Seismic wave velocity. That's the last thing we're doing in the last 5 minutes. I'm going to talk to you now in detail about seismic wave velocities. Seismic means earthquake. Waves means the energy coming away from an earthquake, coming through the crust. And what does velocity mean? Speed, okay? So we're going to study the speed at which these seismic waves travel through the Earth's crust, or the mantle, or the lithosphere, or the asthenosphere. So we can say something about these different layers without ever being down there by studying their wave velocities. What is this one? I guess just showing that we have a slow layer versus a fast layer. That the composition or the physical properties of those layers are different because they allow waves to travel through them faster or slower. These are all great animations from a YouTube channel called Iris Earthquake Science, in case you're really into this. I-R-I-S, all capital letters. I-R-I-S, Earthquake Science. There's many excellent videos there. So back to our story. What page is this? 17, thank you. What's the title for page 17? Earth interior by chemical composition or silica composition. So I'm going to verbally give you and then show you the seismic wave velocities for the Earth's crust compared to the Earth's mantle. And guess who figured it out? Mahorovicic. I won't do it again. It didn't work. Okay. The average seismic wave velocity through the crust, ready? You can write it right on there if you want. 6 kilometers per second. The crust of the Earth has an average seismic wave velocity of 6 kilometers per second. The average seismic wave velocity through the mantle, 8 kilometers per second. 6 kilometers per second through the crust, 8 kilometers per second through the mantle. Are the waves traveling faster or slower? Is it the crust or the mantle where the waves are traveling faster? The mantle. 8 kilometers per second is faster than 6 kilometers per second, right? If you really think about it, that's pretty damn fast anyway, right? But the waves are traveling faster through the mantle than through the crust. Who's thoroughly wide awake? Hopefully most of you. Can you think on your feet? What is the relationship between seismic wave velocity and silica content? Can anybody put it into words? I don't like the word dense, but let's try something else. Do it again, though. Silica content, right? So you're saying if you have lower silica like the mantle, you have faster, right? So here's the relationship. Thank you, Isaac/Aiden. The higher the silica, the slower the seismic wave velocity. The higher the silica, the slower the seismic wave velocity. For instance, the crust. The crust has high silica, but it's only 6 kilometers per second. Compared to what? Compared to the mantle. The mantle, we jump down to the mantle, right below the moho. We lowered the silica in the mantle, right? We decided mantle had medium silica versus high silica. But we increased the velocity. It's 8 kilometers per second through the mantle versus the crust. Do you have it? I'll say it one more time. The crust has high silica and slow waves. The mantle has lower silica and faster wave velocities. 6 kilometers per second versus 8 kilometers per second. The thing that Dr. Mohorovičić was able to show us is that it's not a gradual transition. It's bam. A seismic wave crosses the moho and it suddenly accelerates if it's going into the mantle or suddenly decelerates if it goes back into the crust. You want to see that? Let's do it. Oh, there it is in black and white, or colors. The light blue is 6 kilometers per second through the crust. The darker blue is 8, ignore the 7, 8 kilometers per second through the mantle. We got it? Feeling okay? If you just step back and start kind of zoning out, it sounds super hard, but I'm just saying the same thing over and over again. I thought I had an animation. I guess I don't. Sorry. So in this case, the earthquake is here. The waves travel away from the earthquake happens. Light blue is slow, darker blue is fast, and then it crosses the moho again and slows back down again as it waves back to the surface. Questions? We can say something meaningful about these differences of these layers without actually being down there. And by the way, in case you're curious, we have studied different compositions of materials in labs around the world and sent things through them at different speeds or calculated the different speeds to come up with the relationship of lower silica means higher seismic speed. Same concepts were applied to come up with this lithosphere thing. I don't think we need to look at the plot there, but it's also a seismic wave velocity thing. So we finish where we wanted to finish today, and we're going to finish with, I'm already out of time. Give me 1 minute. This is a first look at a map of tectonic plates. Can you give me 20 more seconds? And this is the same look as page 19. Page 19 is one of the most important maps or pages in your yellow book, page 19. It's a map of the tectonic plates of our planet. And according to today's lecture, It's a map of individual blocks of lithosphere. And so we have a whole new geography to learn. We're not going to ask Tim to point out stuff anymore because that's not a map of the plates. That's a map of the continents. We actually don't care about a map of the continents that much anymore because almost all earthquakes and almost all volcanoes are happening at the edges of plates, not at the edges of continents. And we'll dive into seafloor spreading and all sorts of good plate tectonic stuff on Monday. And you and I will just wink at each other on Monday in a non-creepy way because you and I know this stuff today. And the rest of the folks who are going to show up all bright and bushy-tailed on Monday, they're going to be out of it because we're going to refer to this stuff over and over and over again. So good job by you. Thank you for coming today. I love you. Have a good weekend. I'll see you on Monday. Goodbye. I'll be with you in a couple of minutes. Thank you for joining us. That's the 7th time I've said that. Cookies by Joe. I don't want to eat these. Pedro, you going to help me? Somebody going to help me with these? There's a chocolate chip, like 3 chocolate chip and two dark. Attaboy, Casey. Attaboy. Attaboy. See you Monday. Hope that girl. Good, 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 good. Emily 2, goodbye. Emily 1, goodbye. We good, Ave? We good, Jordan? Okay. Okay.
Oh, I'm taking a chocolate chip.
Attaboy. Okay. We can do a few live Q&As if you like. More than 900 people here still. That's good. Excuse me. Hi, Eve.
I was just wondering when your office hours were.
Kind of by appointment. So did you want to chat Monday?
Yeah, I would do that. I was wondering if I could just take a picture of the drop-in.
Oh, yeah. Oh, the lab room's open too, and these are posted all through the lab room, but absolutely. And you know how to find me any morning, starting at 9:30. So let's just use one of those times to visit.
Thank you.
Okay, you bet. All right. If you already typed in your question, I probably missed it, but let's go back. I'll go back and Linda, it's got something to do with the Earth's magnetic field. That's all I know. I'm sure if you go to movaglobes.com, they've got the details for you on what powers the globe. Richard, is the wave velocity difference due to the substitution of mafic minerals for silicious minerals? Well, there is a chemistry difference. I don't think I have the chemistry and physics background to technically explain why the velocity differences are so distinct. So I'm sorry, I guess I don't have an answer for you. Carol, so how does the New Madrid earthquakes happen? Old plate boundary down there or question mark? I've done a lot of live streams since March, and the craters of the moon in Idaho became a running joke because so many people ask about it, like legitimately ask about it. It doesn't even seem to matter what the topic is. Like before it became a joke. And this New Madrid earthquake thing is kind of a pretty close second. I don't know anything about the New Madrid. I mean, I know the 3 biggest earthquakes in U.S. history were in 1811 and 1812 on that New Madrid fault. But it's been 30 years since I've lived back there, and back then there wasn't much to say about why those earthquakes happened. And I still don't think we know. But maybe somebody has something they can send me that's a major leap forward, but it's a mystery. I mean, there's a lot of mysteries with earthquakes. And if you listen or follow somebody on the internet who says there aren't any mysteries with earthquakes and they have it all figured out, you're being sold a bill of goods. If you're in science and there's no uncertainty or mystery, then you're not listening to a science person, because that's not how science works. So I don't know, Carol. Kyle, is there an animation you know of showing the next 200 million years of plate movement? Yes, yes, there is. Can I spell his name correctly? Christopher Scottese. I think that's the way how to spell it. He's a geologist who has a long career, and he has an excellent YouTube channel with all sorts of animations looking at the past, but also looking to the future. Christopher Scottese, you'll enjoy that if you haven't seen those before. Let me go down to live. Have you correct? Is that correct or not correct? Oh, it's not correct. Scottese. Thank you for the correction. I emailed him last spring when I was kind of trumping up his channel, and he sent back a very nice email. But his work is excellent. All right, let me go back here again a little bit. Kent, is the Earth cooling? Yeah, I guess it is. But again, I don't think about, I don't think much about planetary science, and therefore don't thinking of our Earth as a planet with that range of time and cooling and evolution and segregation of materials. I'm very weak on that line of thinking. Joseph, thanks for the cookies, Joe. Any idea why India moved faster and further during Pangea separation? Well, again, you're listening to me. Now, part of it is I'm ignorant on the latest in geophysics, the latest in Earth interior, although there's a portion of the Earth interior that I became very excited about last fall with the discovery of subducted lithospheric plates that are now hanging in the lower mantle. And I don't know if I'll do much of that in this class. But overall, I don't know a whole lot. So part of it is me being out of step. But I think if there were significant advances in understanding the Earth's interior, and what was your question again? Why did India move faster? Basically, why did that plate move faster than other plates? Again, you're hearing it from me. I don't think we still understand why these plates are moving. So therefore, how can we explain why one plate's been moving faster than another? It's possible I'm out to lunch, but it's also possible that messages that are reported to you with a certain amount of confidence and certainty are not being reported accurately. I don't know if you can tell. I'm out of my element here a little bit. This is physics, not easy for me. Deb, how long will it take to reform the next Pangea? Well, one way to answer that is to just look at what Christopher Scottese's animations show, which is based on good science. He does show the Pacific. I'm looking at the world map over there. He does show the Pacific closing, I think. I don't have a number for you. 500 million years from now? I don't know. Less? The dates that we do know about the supercontinent cycle. Remember, I shared 3 supercontinents with the students this morning. there's not a regular timing of those three. So you can't really just do what you would like to do, which is just look at the past supercontinent we know and just calculate it. Some of you are talking about some of the, what was her name? Karen Siglock stuff that we were doing last fall. I'm skipping some of these questions because I don't have anything intelligent to say. I hope you understand. Dave, does the temperature of the layers affect the seismic wave velocity? Probably. I'm hesitating because I don't want to spread misinformation. And when I'm weak on a topic, I try to keep my mouth shut. So I'm going to continue to scroll. Sorry. I shouldn't have had a live question and answer session this morning, I guess. These are excellent questions, and I don't have answers. Alan, is it possible that the island popping up by Panama is a large igneous province? Yes, it is. Thank you. Large igneous provinces are these amazing accumulations of typically basalt forming very quickly, and a whole oceanic plateau, sometimes an oceanic plateau converting into an actual kind of massive land area that's above sea level. And I just started to learn a bit about those last fall when talking about Silesia, or one of those exotic terrains, Cache Creek, I guess, and Rangelia. And so you're reminding me that I think there is a story about a large igneous province and the root of Central America. Maybe somebody here has got a tip or two. You know, we're starting to get into kind of what we were doing last fall, where I confess a bunch of ignorance and then people send me a bunch of stuff and I learn. I don't know if I have quite the time this quarter like I had last year, but I'm sure some here know more. I'm sure, well, that's true anytime. I'm sure people here know more than I about some of this. Is the next supercontinent named Bob? I don't think so. Couple more, because I'm not sure I'm being very helpful here this morning. Yeah. Part of this is a little premature. We're going to get into some of this. So I think the next couple of lectures will address some of these questions. And many of the other questions, I don't know the answers to. So this is always one of those lectures that I feel kind of works, but I know my limits with this one. And there's a lot to learn for science, but there's also a lot to learn personally. It's never been huge on my list of priorities, obviously. So with that kind of weird ending, the rest of the cookies are gone. I have my green shirt. I don't look yellow today, so maybe I'm going to avoid blue shirts, and we'll see if that works. A toast to you. It's Friday. Maybe I should have brought in something else to toast you on Friday. I guess it's not Friday afternoon, and I guess I'm at school. That wouldn't be appropriate. Here's to you. Here's to the health of your family and your friends, near and far. Gesundheit. Here's to learning new things, never having it all figured out. Always have plenty of things to be curious about. and setting time aside to enjoy the learning process. That's part of what we're trying to do here with young people. You're never done learning, and hopefully your presence here is getting that message across to them. People want to keep learning, even if they're old. I'm old. Most of you are old. We're old, but we're not done learning. Here's to us. Okay, 4 lectures next week, Monday, Tuesday, Thursday, Friday. I'll look for you on Monday. Have a good weekend. I love you, and goodbye. End stream. A large fry, strawberry shake, and a Happy Meal.